And continuing on with our discussion of conjugate gradient, where we left off last was producing this iteration scheme for our iteration vectors represented as x and then indexed with the k. So xk plus 1. Iterate is obtained from the previous one plus alpha k weight times the direction vector pk. We're using the same ratio for steepest descent. That is the parameter alpha k that we use. But with conjugate gradient, the search directions are updated as updates to the residuals. Pk plus 1 is rk plus 1 plus this scalar beta k times the current direction pk. And what we left off was coming up with this derivation of what that ratio should be for beta k. So the idea is that you initially choose your initial gas, compute the residual with the first residual R0 is computed using that first gas, and then we will use that initial R0 as the first direction vector. And again, that R0, that initial residual, will be help generate the Krylov subspace that these directions will be part of. So given the previous lemma on orthogonality in your notes, with regard to the, say, the kth residual vector, rk, we know that all of those residual vectors are orthogonal or conjugate to the direction vectors, as well as mutually to themselves. So all the residuals themselves are orthogonal, and they are orthogonal to the direction vectors. What we also showed is that, and hence the name conjugate gradient, is that the direction vectors pk themselves satisfy this a conjugate condition where that pk Hermitian transpose a pj is always equal to 0, right, for any of the k's and j's. So they are what we say a conjugate. Well, it's interesting that if you take this lemma, which is extremely important in terms of the properties of the residuals and the direction vectors for conjugate gradient, you could exploit that lemma to derive actually a more simpler formula, which Bjork does in the book, for that beta k parameter, which is necessary to update your direction vectors. In fact, you can show that that beta k value is this simple ratio, where all you need to do is take the square of the 2 norm of the updated residual and the previous one, so the rk, so the 2 norm squared of that. So just those ratios of norms of your residual vectors, the previous one and at the update, is very simple. It's a very simple way of producing that beta k parameter that you need. So what I'm going to do now is I'm actually going to write out sort of a Matlab-style CG method so that we can see how to put this iterative method to work. And then we'll talk a little bit about the rate of convergence of the conjugate gradient method. So, so here we go. We'll just sort of represent, like I said, in a MATLAB kind of style here, what the method would look like. So in MATLAB, we might say we're declaring a function which will take on an initial guess, produce, the output would be our approximate solution and the residual using that, and we'll call the method CG, and the input should be the coefficient matrix, the right-hand side, an initial guess, we'll call it x0, so that's a 0 there, and then maybe, since we may define a maximum number of iterations that we might want to iterate to, sort of to iterate to that. And there's different ways you can have stopping criteria for CG in terms of looking at progress that's being made. But for now, we're just trying to see how we would code this up. So first of all, what we're going to do is take your initial guess. So the x vector will be running through the code, and we'll initially use our initial guess to the solution as x0. We will compute a residual. We'll store that in the R vector. And again, that would be a times, again, this is Matlab-style code with the asterisk for times x0, semicolon. We use the first direction vector as the residual, and we'll call that P, and we'll store that. We'll store R in that. And we're going to need some norm information later to update the beta K. So we'll go ahead and compute R transpose R, if we're in the spirit of trying to get the 2 norm, and we'll call that variable RTR. And that will just be R transpose with the apostrophe in MATLAB time star R, okay? And we're ready to go. So what we'll do now is we'll start a loop, and we'll use the same indexing integer that we have in the theory. We'll let k run up to the maximum number of iterations, and then we're going to just write this loop. It's very clear we need matrix multiplication. We need A times the direction vector. Let's store that into a vector called Q. So we need to multiply the direction, the current direction, times A. All right. Now we need the alpha value to update our iterates, so we'll call that, guess what, alpha. And alpha will be RTR. We need that. It's, if you go back to the notes, this the numerator term. And we will divide it by P transpose times Q. Of course, Q stores A times P. So that would get us the correct alpha K parameter that steepest descent produced. Go ahead and update your guess. Again, we don't need to index. I'm saving storage here by just using the vector x and updating itself with the new iterate. And so it would just be an update to itself plus alpha times P. And there it is, very simple. Now we need to work on updating our residual as well as our direction vector. So the residual can be updated very simply as R is updated as R minus alpha times Q. That's the update of the residual. And again, we're going to have to, for beta purposes, we have to have the old iterate R sub k, the 2 norm of R sub k, and then also in the numerator we're going to need, remember, the 2 norm of R k plus 1. So we will store, let's say, RTR old, okay, as this residual, is our RTR that we had up here, because this is, again, this was determined before we did an update of the residual. This is the new residual value. So now RTR will be using the current R that's been updated. So see the difference between that. So this will essentially get us, if you go back to the notes there on the previous page, this is getting us that denominator term related to RK squared of the 2 norm there of RK. And this value here with the updated R is basically getting you RK plus 1 2 norm squared. Okay. So now we're in the position of producing the beta parameter. So we will go ahead and use beta. And then beta has to be the new RTR divided by the old RTR old, semicolon. Now we have the beta parameter. Again, this is essentially just beta k is what we've produced there. And now we're able to go ahead and update the search direction, which is take the residual in the direction of P scaled by beta, okay? And that's it. In the loop here, okay, so we have the entire for loop now in the CG iteration there. And this particular code would just run up to the max number of iterations. Again, there's different ways you could implement stopping criteria in terms of the residual or the convergence of the iterates x themselves, right? But the beautiful thing is the storage is minimal here because we are using one vector R to hold all the residuals, one array x, or vector x to hold all of the successive iterates, and similarly, just one array or to hold all the directions. So this is an extremely efficient method. Most of the complexity of the iteration of CG is right here in that matrix vector multiplication. That's where most of the complexity is. All right. So really a wonderful method, very, very easy to implement. And what I'd like to do now is just briefly talk about some of the convergence properties of the method. So this would be the next section of Bjork's book, and so this would be section 4.2.4 on the rate of convergence. of the CG method. Okay, so as I mentioned in class, in exact arithmetic, if you were looking at things exactly with no catastrophic errors and no round-off errors accumulating, CG actually, because in the sense that those residual vectors become an orthogonal basis for your Krylov subspace, in fact, you should be able to converge exactly to the exact solution in n steps. So in exact arithmetic, conjugate gradient was considered originally a direct method. So it was considered a direct method because it's guaranteed to converge in n iterations. So that's what we mean. Converges in exact arithmetic, it converges in n iterations. Now, keep in mind, if you're solving a 10,000 by 10,000 system, we're talking about converging in 10,000 iterations. And typically, as we talked about with projection methods, we really don't want to iterate to that many steps. And in fact, we never would do that with conjugate gradient either. But it's just interesting to know that theoretically, it is guaranteed to converge in n steps. Right? It usually takes more than, again, it varies according to how conditioning, how much conditioning you have in the coefficient matrix. The eigenvalues definitely affect it, and that's what we want to recall. Okay, so let's recall, if we're talking about rates of convergence, let's recall that CG is minimizing or minimizes the norm, the energy norm, we'll say, of some polynomial in A. We'll call it, oh, this was K, I'm sorry. This was QK, if you go back to the notes, QK of A, some polynomial of degree K, minus the error of the initial error, right? And we're applying the energy norm to it. So that's what CG really minimizes, all right? And that's over all residual polynomials of degree K. So what we can do, though, is we can use the eigenvalues. Again, this is in terms of convergence properties. Spectral information, as you recall, I've said many times, determines everything usually. So we can use the eigenvalues of the original matrix, the eigenvalues of A, and abound on QA. And say abound on actually taking that polynomial and looking at bounding it in terms of an eigenvalue. So we're going to look at this function qk of lambda, where lambda is an eigenvalue of A. I'm going to write E value. To obtain the following bound. Not just any bound, it's an upper bound. So I'll put that in parentheses. So what can be shown is that the distance of that iterate, the kth iterate, the x of k from, let's say, the exact solution x star, evaluated using your energy norm, will turn out to be in a very similar way that we had before with steepest descent. You will have a constant 2 factor here, parentheses, square root of k, capital K here, this is not the little k, minus 1 over the square root of capital K, plus 1, the roots just, the k is just the roots. Then you have your little k here as the exponent, times the original error in terms of the guess that you took, how far away it was from the exact solution in the energy norm. And of course, this is the conditioning again. So this capital K is the separation of your eigenvalues, okay? You can look at it as how far away the largest is from the smallest, okay? And that should be the largest to the smallest, like this, okay? Like we had before, exactly like we had before with the steepest descent. And of course, you could look at that parenthetical term there if you want to. If you wanted to get another way to look at this, you could also look at that in parentheses terms as 1 minus 2 over the square root of capital K plus 1. And again, that's going to be evaluated at K. Right. So what you can see here is, again, here's the issue of conditioning. The rate that you're going to drop is still very much dependent upon the conditioning of your system. Okay, so we'd really want to get this far away from 1 in many ways, and so that this rate of convergence in terms about the relative error that you're going to get as this iteration proceeds is now bounded by 2 times this quantity to the K. Really like this value to get very much less than 1. Okay. So, and if you go back and compare your results with the steepest descent bound that we had, you'll notice the difference being this constant 2 is very much different. But it's still very similar, that the convergence is very much controlled by the conditioning of the problem, okay? But the way the directions are chosen now for conjugate gradient are much different than we had with steepest descent. So one thing that's a very special case that I'll mention, which is sometimes important, is that typically CG is very effective for certain problems with the following property. It's very effective when A, your original system coefficient matrix, when A is a low rank perturbation, is a low rank perturbation of the identity matrix. So what I'm talking about is there's sometimes in signal processing and a lot of other applications related to electrical components, you might see the iteration matrix looking something like this. It's a perturbation. So again, we're looking, it could be in the complex but square case of square complex matrices. But this perturbation is done in a way that the rank of this matrix B, let's say, is, we could go ahead and use P, for example, but it's much, much less than N, right? Where your original system lives in in C N by N. Okay. So it's just very interesting. If you have this particular case, CG tends to converge very, very quickly. One advantage with regard to your spectral information related to this is if your system, if your coefficient matrix has that property, it's not too hard to show that that matrix A could have at most P plus 1 distinct eigenvalues. In other words, of the form 1 plus lambda I, for I goes from 1 to up through P. It's because of the fact that you have the rank perturbation, and this is rank P. It's not too hard to show that all the eigenvalues will be of the form, of course, the eigenvalues of infinity are all 1, so 1 plus some other value, and you'll have at most P plus 1 distinct eigenvalues. So effectively, in summary, in this particular case, what this means, push this up a little bit, is that conjugate gradient in exact arithmetic in such a case would require at most P plus 1 iterations to solve AX equals B. In other words, the Krylov subspace would turn out to be of that size, P plus 1, and if by just continuing iteration, you're not going to be able to expand the subspace. It's just going to become what we call an invariant subspace. It won't grow any larger. And that's simply because you're able to construct this problem, so this is rank P. So the fact there's only P, at most P distinct eigenvalues would dictate the largest number of iterations that the method's going to take. It's really an interesting problem. Not every problem has this kind of situation, but it tends to be very, very effective in these cases.